All right, hello everyone. Welcome to today's seminar. I have Vishvas Pandey from Fermilab talk to us about neutrino-nucleus interactions and precision and new physics searches at neutrino experiments. Take it away.
Thank you so much. Thank you so much for the invitation. It's a pleasure to be here. I was here a couple of years ago for the workshop, workshop, to come back, see some familiar people and some new people. So thank you. Also, I feel it's almost my fault to bring cold here. Okay, so I'm going to talk about neutrino interactions. Request for new such as neutrino experiments. It's pretty long title. So I will discuss a bit. I'm talking about a request of looking for new physics at accelerator-based experiments. As far as we know, is now kind of established, right? We agree on it. And I think the internal facilities, we think that we are at the beginning of the universe. I will go with neutrinos, the really known factor, model. New physics, various kinds and sizes of neutrino to answer many questions, for example, the origin and nature of neutrino mass. We don't know why neutrino mass so it's smaller compared to other leptons. Also, we know neutrino oscillates, so we have experiments that for short and long baseline oscillations use that for the heat flavor of neutrinos, determine neutrino mass hierarchy, CB symmetry violation in the neutrino sector. Also, the kind of facilities that we have intense beam and the kind of detectors we are building very sensitive, very precise, and so on. They could also be a great place for probing dark sector physics signals at this. Of experiments are in astronomy in terms of supernova. So this is general interest, right, of this community. And my scope of my talk is a constraint from tens of MeV to a few GeV scale of neutrinos. We're not covering ice cubes and so on. There are two kind of sources that I will discuss today. One of them is the neutrinos from tens of MeV energies. Those are either produced at the SNS, so-called the decay at rest neutrinos, right? Time decay at rest. At SNS, Oakridge Lab, or Lance at Hamel, or Gaypar, the photo is pretty short together. Where we have a proton EV or lower target, produces some pions and chaos, so on. The pion decay at rest produces the nu 30 MeV, and then the muon decays further into nu and nu bar. Incidentally, from supernova, Proclus supernova, also produce neutrinos of the same energy. It is also they complemented with these two sources. I will also discuss a bit about that. And our typical accelerator-based neutrino sources, decay flight, parent decay flight neutrinos, from something with a few GeV, the kind of one we have at Fermilab, BNB, NUMI, and future LBNF at Fermilab, as well as the same part, where we have higher energy of proton hitting a target. Here we have magnetic focusing hard to focus the orbiting pions to try to focus the neutrino beam. And we have our neutrino beams are then of the order of hundreds of MeV to few GeV. That's the energy range that I'm interested in. And the kind of physics we can probe here is pretty broad. Physics, BSM physics, cinematic precision test, as nuclear physics. So there's a lot we can do here. And the focus of this talk is how to make all those new physics scenarios and everything more precise and so on. So one of the main hurdles we have seen in the current experiment. So the current experiment from T2K and NOVA. One of the largest systematic uncertainty in these experiments, for example, T2K here is the NOVA, comes from neutrino-nucleus cross sections, right? As we go to the next generation of neutrino experiments, HEPEC and DONE, the statistics will significantly increase. We have bigger detector and so on. So we will decrease this bar here, and we have to now. This will be a limiting factor systematic, right? By not reducing the systematics, it not only delay physics results by years, but it could also be difference between achieving or missing discovery level. Yes.
You might not know. NOVA The biggest systematic is this detector calibration. What do they mean by that?
I think it's just all the unknowns in the detector, right? How the detector calibration, so how the detector, let's say, for example, in silicon PPP, right, when the neutrino hits the target, produces charged particles, they don't move towards the anode plane, right? There are lots of effects, detector effects, for example, the argon ions can all combine together and affect how the electron or space charge effect, right? It's similarly a lot of other effects that affect the detector capability, right? Those are all the things that people play with and try to calibrate detector. And one could calibrate detector with own source. Let's say you can, let's say SVN or micro cosmic muons to calibrate those things, or in small experiments like CCM or so on, we an inject a source of neutrino or something. Anyway, that comes from both detector physics, some expertise. But yeah, that's big. Because actually, micro, I don't know if you have for sure. From their first generation results to now, this bar has decreased a lot. It's a lot of work in understanding the detector and trying to reduce this more and more. My hope is microphone sorting on this thing as down. This will be hopefully smaller, particular and yeah, this is very good. Similar things also similar issues exist also at lower energies. So then some for example, if supernova happens, the UV supernova, you want to detect them at doom, they then some neutrinos, you want to detect them at doom by this UV charge current process. The processing for this process is really not well known at all. You can see many equations here, they differ from each other orders of magnitude. They are not there on. And there is a study on how well we can listen the cross section to to understand the supernova physics that Dune, it says current understanding of processing is inadequate. Measuring, for example, energy release to 10% will require 5% knowledge of the process. Also, major differences with no data. So it's a lot of understanding. Also, gives low energies. Similarly, for sevens, I'll talk about this as well. For sevens, the cross section is a lot smaller, only a few orders, few percent, at least for the decay at rest, below 50 MeV and so on. But also the physics of the BB after is also the new physics is a percent labor difference. So this still be a lot smaller, but still a challenge. How does this enter into our typical neutrino oscillation experiment? The cross-section surety. The way we do oscillation experiments is we produce the neutrinos. We put a near reactor close to it. So, for example, in two, we produce the Fermilab and have a near reactor complex at Fermilab and we measure the event rate. Then will be a combination of the flux and the cross section and vector effects. And then let the neutrino travel and let's say some of the point vector is fused. We will also measure the event rate at the point vector. That will be again combination of the flux, cross section, the vector effect. At this time, there's also probability of oscillation. In principle, people in the past thought you can take the ratio of the two, everything cancels out, and you can extract the oscillation problem. Right? People who are cross section have always been saying you can't do this, you can't do this because it's a lot more complex. It took us many years to convince the community. Now everybody agrees. Let's cancel this out, at least in the long baseline broadband fluxes, because for many reasons, flux and cross sections are convoluted, right? There's different neutrino flavors at near and far vector. If it's the appearance search, lots of different energy spectrum at near and far vector, because in near vector you have unoscillated flux, and the far vector the flux is already oscillating. You also don't have the identical detector near and far, so you just can't cancel this out, which is your respective cross section kinetics. Also more directly, oscillation probability is not controllable, and we don't know that. This is how for example, for Doom, this is the right? This is how flux is pretty broad. If you really right, it's a pretty broad flux. We don't know the energy a priori. The only way we can constrain is by letting the neutrino interact in a vector, and whatever information we have, we can reconstruct it. And that will depend on our detector's capability. There's two possibilities. One is doing this using kinematic method. So let's say for HEPEC, the Cherenkov detector, you will see maybe a new one. or calorimetric method, the way we can do in dual liquid TPC, where we can see all the particles. In the calorimetric method, let's say in HEPEC, you will have helium proton interact with the argon nucleus, we produce a carbon nucleus and oxygen in the paraductor. There's a muon if it's a charge current process, and you will not see any other particles. And you can assume that if you only see a muon, this is a kind of CCQ, so charge current quasi-elastic, which means a nucleon versus a knocked out topology. And if you do that, you can actually reconstruct the neutrino energy by this formula, except that the nuclear effects will mess things up here, because if you see only a muon, assume it's a 1 muon 0 pion event, that we have contribution from two protons going out, which also you have no information about, as well as some FSI effects. For example, a pion is produced, but absorbed, we don't see that. All these effects have to be taken into account. So we can't really construct modeling. Same for, let's say, for dual, we can see all the particles in the state. So if you see the sum all the energy and the reconstruct, because we still have some missing energy electrons. We can neutrons some level of these very complicated, as well as the same issues if the particles are below threshold of the detector. You don't really see it as the FSI effects. If the pion is for example, the pion is produced with is absorbed in the nucleus, didn't show up in the detector, you will not have any idea how to reconstruct. So all these effects requires that we need to know neutrino-nucleus cross section given the flux and the target in advance of the operation.
Still, I have a question on the previous slide. Do neutrinos detect the neutron?
So not directly, because it only sees the charged particles, right? It's a TPC, it's a cathode where electrons drifts. It only see neutrons indirectly. For example, if neutrons
It's a proton.
exactly hits a proton and produces a blip.
Low efficiency.
Yes, and it's also difficult to. We don't know how far it will travel. We can actually make a circle around the vertex, but not travel far and so on. But yes, by charge exchange or sending the argon nucleus de-exciting goes on. Like a spin program, we are working on improving this thing, detector. Similarly, for oxygen physics, physics at our facilities, the way we produce neutrinos, hitting a very intense proton beam target, putting charge and neutral mesons that decay neutrinos. Those can also produce some exotic particles and some detector particles, and they can mix with the carbon mixing with the smaller particles. Those particles can go to a detector, either scatter or decay. The signals of those particles are very similar to the signals of neutrino interactions. So it's in our process to gain some physics, we need to constrain the background of neutrino interactions as well. So with that, this is the first part of the talk. Motivating. We need to constrain neutrino interactions to do oscillation physics, to do baseline physics, and so on. So what is neutrino interactions and why is it complex, right? This is typically how our neutrino electromagnetic interaction with the nucleus, electromagnetic weak interaction with the nucleus looks like as a function of how energy transfer to the nucleus. The energy transfer is very small. Your degrees of freedom is nucleus itself. You have elastics, the sevens kind of peak. Your probe sees the whole nucleus. And if the energy is tiny bit more higher, it sees the structure inside the probe will see the structure inside the nucleus and can excite the nucleus. So only if the energy is high enough of order of nucleon, your degrees of freedom now start to happen are nucleons, and you can have positive peak with a single nucleon knockdown, or you can have different with two nucleons which are equal to each other and the wave functions can overlap or can produce, or there is a bit more higher to excite the nucleus to many resonances, delta, and so on, and produce pions and hyperons. Based on the hyperons, only if the energy is very high enough, the probe can see the quark inside the nucleons, and you can do it mathematical. So this reason in between the Reed-Lansky scattering and all this, there is a unified theory to describe between the interactions. You need to rely on many approximations, and it's basically a quantum mechanical many body problem in main nucleus and nucleus, right? It's multi-scale, many body problem, subject to structure and dynamics, as well as the interaction between different degrees of freedom. We have going from nucleus to nucleons to quark. So there is a many degrees of freedom that your interaction process spans. Typically, the way nuclear physicists study this region, they take omega, take energy, and you study that region, right? Let's say experiment J level, so on. With omega here, or here, right? You don't have everything together, which is the problem with the neutrino experiment. We have broadband flux, so it's we have the flux which covers the both elastic and inelastic part here, and then you so on. You have a pretty broad band. So you have all the processes together in your interactions. This is one example. If the neutrino beam was monoenergetic, so 3.34 peak of linear flux, you will be able to separate this as a function of interaction. You will be able to separate different mechanisms by looking at the energy of the neutron. First, we get the full broadband flux that from here. Everything that we look at. So in order to do this, we need everything comes everywhere all at once. That's a problem. Each of these energy regions requires knowledge of nuclear ground state, electrical response, and the propagation of the nucleons or hadrons inside the nuclear medium. So also the fact that challenging. So you have more holistic process, combine them together, there's no double counting and so on. Our problem is we need to know everything everywhere at once. That's our problem. So what we need to do, this is the wish list of people. We need to be a custom model for international physics that covers wide transfer for for this experiment. For main API, I think for Origin, for the this program, and carbon for HEPEC, all the different antenna flavors as well. For let's say operating structures, you need to cost and differences. There's a letter universality, but there is a letter mass effect, and very present impact the process. And I will talk about that. This is also not trivial that low energy new crossing different. For research, you need to constrain the neutrino and antineutrino differences, right? Especially they are especially relevant for isospin acidic nucleus like argon, with a different number of neutrons and protons. So neutrinos will interact with the 22 neutrons, and antineutrino will interact with 18 protons. That's a different physics. And for all the Paschen observables, it's in principle all the models should be validated against existing data on electron scattering, so extra data. Allow estimation of superconductivity, as well as allow robust implementation into having the model and putting the generator so that experiments can actually use it. This whole endeavor requires the work of many different communities. So I made a chart where it shows how many different communities has to work together to solve this problem. And in recent years, many of us are working in overlap of many of these things to many of these communities to solve this problem. We need a nucleon label, we need precise calculations from radius QCD, and we need data on our target. To obtain that, they need to put your nucleon into a nuclear very quantum mechanical theory, right? And that has to be constant with the data on the scattering or different scattering. And that has to many communities has to work together. This is a challenge problem. It requires the benefit from expertise on high energy physics and so on. Otherwise, collaboration between theories and experimentalists. And then another part also in SNOMAS, the emphasize on this. So that is one bottleneck. Many of us work in a office field and small communities to solve the problem. Now, moving to the third part of the talk, I will give some examples of the recent developments on theory side, experimental side, and generator side. I'll start with more time on the low energy, and then I'll run through the energy part. And finally, I want to talk about go with all these figures, but it's not enough time, so I'll try to give a glimpse of movements in different parts. Let's talk about the low energy part first. This is, as discussed before, this is relevant for characterized kind of sources, as well as for supernova neutrinos. At this energy, they do kind of various neutrinos can interact with the nucleus, either elastic scattering, we call it sevens, or elastic interactions, scattering, where it interacts with the nucleus through by the so it's a neutrino process, and finally the nucleus is in ground state. They just the elastic scattering, so it almost just does, it stays, it doesn't change, it's it doesn't excite to a different state. And only observable is very tiny recoil energy that is left in the detector. But the constant for this process is very high. It's elastic speed, right? While for the inelastic case, the neutrino can excite the nucleus to the neutrino has this access to the internal structure of the nucleus, excite the nucleus to well-defined states that can be powered by the acceleration gamma or neutron proton the nucleus fragmentation in the nucleus. The cross section for this process sevens is a lot higher than the inelastic process, which I shall try. But at least at this maybe scale, this is why I want to actually build a small vector to do some physics. That's how well we know these processes. In order to compute this cross section, you one element which has a convolution of the electronic tension of the electronic vortex, the hadron vortex, right? You are basically computing the current around between the different initial electronic state. In the sevens case, this is just the time between the ground state. So your cross section simplified and reduced to just a weak form factor, right? While for the inelastic case, you are assigning nucleus to the final state, and your clock expansion of the full matrix element, which has many transform transport. So it becomes more complex here. Let's talk about elastic first, and then we talk about inelastic. So the elastic cross section in the tree level, it's just in proportion to the weak form factor. All the hard problem goes here. The big form factor can be written in many different ways. One way is write it. It's just the element the ground state. It can be written in terms of the proton and neutron form factors and their weak charges, and then into their densities in the nucleus, and it is assuming it's a spherical nucleus. But the function here. Now, how well we know this quantity is then? First part, so the proton is obviously not very constant. Electron scattering experiments, elastic scattering experiments for decades. This part is very constant, but this part is also smaller because this is reduced by the small value of the big angle. For the neutrons, neutron form factors are a lot less well known. Right? Obviously, neutron is difficult to prove, but the process is more sensitive to the neutron densities. How we can improve that? We learned this paper many years ago. That electronic probes, such as perturbative electron scattering or sevens, would be an ideal probe to determine weak form factors and neutron densities. Right? For decade, it was very difficult. Both of them are very difficult experiments to do. But recent times now we have both experiments possible with all the development technology in years. The current experiment that we has 2017 has demonstrated that they can measure sevens, right? Now there's lots of neutron experiments. We are not talking about ton scale, and this is like 100-ton scale detector, a sevens detector that can be deployed. So this is going well. For that electron scattering experiment, for example, at JLab or at Mines, one could actually measure the periodic asymmetry for the elastic scattering and provide this asymmetry in the factor difference in the cross of positive and negative electron. But because this asymmetry is closer to the weak form factor and top form factor, This piece is well known, so this one can be with this. And there's some little measurement with that. And constant and the big form factor. Only problem is this experiment is only at a given Q square. We like experiments and different Q square constants. If both properties can work together and can try to content the big form factors, but they obviously don't both are driven by different physics, right? Here you want your choice of nucleus is also because you want no liquids and you want low resolve. Here because different nucleus because they want to understand the neutron stars and so on. So both sides are different. By principle, combine the two, but could do content the big form factor in future. But also compare this in manual theory. So we compare this in a model we call Hardy model. What we do, we describe the nucleus in as a many-body system where nucleons are bound to the nucleus in the potential. The potential is carbon. We solve the Hardy equation with the potential to obtain a single nucleon wave function of each nucleons in the nucleus. And by using those wave functions, we can compute the gas base. By that is we can compute the performance of the neutron. You know, it does a pretty good job. So this is compared with organ, our calculations here, and this calculation from our initial defines. They be and that dots are data. Our model describes data pretty well. It's supposed to explode here. It doesn't matter because the silence is only 0.5 into. And for the weak form factor, there's no data on argon, there's data on lead. We have very data which is argon. We also form factors. All these equations are either initio or relativist mean field or shell model or chronological. There's only very few percent of error on this. There's only about 2% affinity on this cross sections. The problem is a lot more control, except any deviation from this cinema predicted either trait, either in the change of either trait or change the shape of the dot spectrum, will be physics. We may still need to have this as much in control as possible to disentangle the physics from physics. Let's talk a bit about the elastic part. As I said before, or in two, UV coming from the low energy gains coming from supernova. In two, we measure them by those UV scattering in the detector and charge current wave. So it's in UVCC this process, and the cross section for this process is not well constant at all. In fact, this is the word data, summary of the all data that is available in elastic scattering of neutrino on any target. There is no data on argon. There is a problem, but to improve the theory, but to propose measurements and improve generators. So I'll talk about it in the next few slides. So we can compute the same elastic cross section as well in the same model. On top of the Hardy experiment, we can now include continuum random phase approximation. So long range correlation with the nucleus. Those correlations allow you to have the structure and predict the low-lying collective expression in the nucleus. The way we do it, we add a local RPS that obtained by iteration of this gain function. This part is not default. There is a potential here, and we create over this, and we make the CRPA prediction, which is some comparison of CRPA with the constant data. And you can see the kind of simple electronic kind of model of CRPA with the presentation. This model actually goes to and the way it's computed for both charge and current, we have we compute the process of each multipoles and then sum it over. The room computing uses Marley. Marley is the event generator that is used to simulate a supernova neutrinos interaction and tune. Marley uses Marley uses supernova approximation. It uses the long wavelength limit, where it predicts kind of simplistic approximation. The predictors in limit as you look at the constant function of electron scattering angle. This is very important to know because this will help us to point the direction supernova came from. Right? Scattering is very important. It predicts a flat distribution, but the our calculation that that shows a more backward kind of scattering. This will be very important for those who know which direction is going from. So we have been working with the Marley colleagues to implement this model into Marley so that Doom can use it. So this is the answer of the speed level with Marley colleagues. Then we added the equipment, the implements and the one thing which changed, I don't know if you people have seen Marley paper before, but good news for Dune is after we put the CRPA, this now shows constant functional energy, and one of the finds gamma or alpha, right? Neutrons are solved for Dune. So if you look at the red ones, which is the neutrons, the dotted ones are English, Marley, and the red one is the Marley after CRPA. Neutron contribution has decreased. That's kind of good news for Dune. Less fraction of neutrons and more gamma and yes.
So if you increase the neutron detection efficiency, I think, then you get full calorimetric. That would actually reduce systematic.
Exactly.
And also especially for supernova, your neutrino detection efficiency goes down with them.
Yeah.
I think the neutron detection will be especially important.
Yeah. And in people reconstructing supernova flux, right? We need to do all, right? So gammas in the detector, neutron, some of the energies, right? Gamma, I think neutron TPC can do really well. As you said, neutrons, the protons and alpha and so on are a lot more. Gamma and neutrons are the main thing, right? And neutron, in the current experiments, in microwave we are working very hard to do neutron detection methods by having the secondary interactions in the but good news, what we see putting a better model looks like less neutrons expected. Of course, we make measurement of this because there is no measurement. Top section, there's few possibilities where it can be done, but it worked at last almost lab. Some of people in the room master part of it. We expect to see events per year, and we already have year beta. And we are currently analyzing it. It will not be. Might not be the best thing to do is if you can make measurement like if you can make this kind of measurement. That's scattering angles. That will be more difficult, but at least we can put some data point here, for example, and that will be very useful. Similarly, for SNS is trying to bring a planet scale detector, a 5x4 agency, and that will be very useful. And also at Fermilab, the new facility called Fermilab facility for dark sector searches, the African discovery. We're planning to put hydrogen liquid argon experiment like cesium, dot reader, as well as proposing to put the liquid on TPC, so that we can measure the cross sections there. This physics, essence of MEB, is also interesting and non-negligible. Even TV scale electron beams that it nice to convince you for that. Let's say if you look at the function of muon energy, or I mean the energy at the peak of the BNB or forward going muons that have contributed to some excitations, even at the SBN. You flux fold it with the whole BNB flux and look at the power of order. These lines are the contributions from way forward to the neutrinos. This part is important from the going excitation. So half of the signal can way forward going with pins from going excitation physics at the energies. And this is also I have like to come back to this. This is also important for the new mu understanding new cross sections at energies, which is important for all of oscillation program. In principle, the new cross section should be very similar, right? But at low energies, where the let's say charge current case, where the electron mass difference, so 100 MeV to less than MeV for electron, but that matters. Your new effects start to play a role. So for here, for 200 MeV neutrinos, the new cross section is not higher than the cross. Here we compare with the different calculations, and they both have similar. So if you are in a region where electron mass matters, and maybe because to produce a muon or electron, to produce a muon in the final state, you need larger moment transfer that affects the problem. And the high enough energy, the low energy is also affects here. There's also another, in principle, a clean signal beyond decay at rest. There is a monoenergetic source, 236 MeV, here at NUV being done by Fermilab or MLF at JPark, where kaons the decay like 60%, 65% ratio. The decay this peak. So this in principle is is subdominant compared to the whole decay and flight flux, but minimum did a very good job in trying to measure it. It was only a shape like measurement. It's interesting because it's 200 MeV. It's not enough to have full coelastic peak. It's not high enough to have full coelastic peak. So this is where both the lower decay and the coelastic peak kind of. So if you compare different calculations, all over the place. Actually, there was a new measurement that they park recently. So we haven't compared it to the very interesting. Now, in the last 5 or 10 minutes of my talk, how much time I have? Oh, awesome. Let me move to the more high energy GeV scale part and just try to give an overview of new developments on the theory side, experimental side, and so on, right? And the cross community work. It has a lot of theoretical development in recent years. We were trying to develop their models, and most models up to now have focused on inclusive reactions. They only look at the final going leptons, while the more data we have from liquid capacities, everywhere, more exclusive. So those perturbations are not there yet. But even if you compare the inclusive ones from different from each other, data has also not been that precise to distinguish between them. So we're hoping with the more high statistic measurement forward, that will be useful. The notable improvement has been on the nucleon side. There is form factor made a lot of differences at the form factors. We were using the deuterium data from bubble chamber with the axial form factor. There's the right here. Now we had calculations, from many different groups. There is QCD. They all can converge, and they all at least work with high Q square are different from the expansion from the variable page. This is a new development, and it's still by the kind of. And there has been lots of a few years ago, I didn't talk and say we need more data. Now there's a lot of data. The theories has to catch up. In recent years, there's lots of measurement, lots of nova and microboom, and more measurements. CNV and so on. So the landscape of experiments are looking very good. We also have been development in some of these models here implemented into more generators, so the experiment directly use it. I give you an example of the CRP being implemented in Mars, where the tool can use it. Similarly, let's say here, Suja version 2, here CRP model, but into Genie. So now the experiments are more in the CNSP, and we are able to use those models. 5 years ago, more good models. There's also the one problem that we have in community, all the vertical generators are written by experimentalists, while otherwise in other communities they were mostly written by theorists. So now we have for generator. I want to talk a bit about the TPC experiment. This is kind of become a game changer in constraining different cross-section. This is the TPC detector we utilize in the current active program formula, which is to set up 3 experiments, FGAP experiment, and the ICARS as a fire detector. We all use TPC. This is a image from microphone. These are like bubble chamber kind of images, but colored. Color means energy deposited, so you can actually do that colorability. This is the real event from microphone where we counts in and proton, and you can see state very nice. And the color here is how much charge deposited, so you can actually reconstruct the energy. This is very well. Using that, microphone has many interesting measurements. And it has its targeted data, and now it's being network. I'll give a couple of examples from microwave, how it will improve using this technology to do some very creative measurements. For example, they look at the events like quasi-elastic kind of events, like proton and muon final state. But they can go beyond that and actually look at the transfers. So if the proton and muon the final state, you can project the momentum to the transfers to the direction of the neutrino beam, right? And the transfers you can sum the kinematic momentum of proton that actually kind of describes the nuclear effects. This kind of measurement you cannot imagine 5 years ago into neutrino experiments. You will just say muon proton and you just make a double diffraction cross segment. Now we can do fun stuff. So it's this kind of measurement clearly shows you look at the dance lines. So the models in GIVU without FSI, so without Pfizer interaction, or with Pfizer interaction. So it shows if the model has, it shows the data has the Pfizer interaction. So before these particles came out, the proton, it was already modified in the target before it came out. So this really distinguishes between data set. And also, microwave has demonstrated that they can do more rare searches. Like here, left is the lambda baryon production, computer suppressed. This is for anti-neutrino part of the beam. This lambda will, so you have a muon charge current process, and the lambda is neutral. This you have a gap. The proton and a pion, and you can see that, and you can reconstruct the embedded mass of the system, and directly peaks where you expect the peak of this lambda. And this bigger, yeah.
Seeing this reminds me, do you think there's feasibility of flavor changing neutral current measurement to be done? Kind of is that precision detector?
In principle, yes. So I think even I think this process as well has could be flavor changing neutral current process. In that case, there will not be any muon, right? So that will be challenging. But in principle, as long as the signals have charged particles, there is no. But the problem with the flavor changing processes are the branching ratios are very small, right?
It's a exceptional background control and precision like this.
But to support your point, even this is a very rare process. Let's say this is mainly induced by anti-neutrino, and the BNB, the anti-neutrino production is only 0.5%. Most of the beam will not produce this. It's 0.5% of the beam that will produce this. So my code has this run only 5 events. They could identify it, and using those 5 events, they can still do this in very mass. So yes, now it's possible to do rare, such as this motivated us. So I wanted to highlight our very recent paper to use this kind of resonance channels to, for example, constrain neutrino flux. So as I said, one of the problems is to how to uncertainties are very high. Typically, people propose that you can actually do neutrino electron scattering, elastic scattering, because the cross section for that is very well known because there's no nuclear physics there. To constrain flux, neutrino flux. But number of events for neutrino electron scattering is a lot smaller. It's like orders of magnitude smaller than the scattering from the nucleus. We pick one of the cross section, neutrino interaction cross section, which is a bit better known and has enough events. That's the charge current coherent pi interaction. It's like kind of coherent process, but in this case, like similar to Siemens, that the fire reductor is still in your nucleus stays in the ground state, but the pion also goes out. And the cross section for this is based on is well known, and you can write from the first you cannot write the Neutrino-nucleus constructions, and they are written from the PCAC, though Friday partly conserved like when you cross and just exactly proportional to the elastic scattering of electron to of ion to the nucleus. That can be constant from external data, and everything else is simple. And we accept that locus and we have demonstrated that this is the black line here is the flux 30 on June, and all the other color lines are if you use the constant flux. It's only possible. We can only say because we see this from microwave. Okay, we can do this kind of things and And now the high statistics and high precision era of neutrino interaction starts with the experiment called Pandey. It's the new detector in the engineering program. And it's currently taking data in neutrino beam since December 9. I think Kevin is also part of the probation. And this experiment will spend, I think, more than 4 months. And we are so close to the target that we expect 2 million events per year, Chapter events, which is amount of events for the neutrino experiment. And we expect 7,000 interactions every day. Let's say we're setting data on number 9, 7,000 interactions every day. These are corrections on one day data. And by 5 years, in 3 months, it's going to be the proof from now, we will have data as micro inside. This will allow us to do, let's say if you look at photoelastic or 1.0, 2.0, and so on, we still have millions of events in all of these final states. So we will be able to do, this shows the statistical uncertainty is going to be really small, and we'll be able to do a very interesting process. With it, I have more minutes. I want to talk a bit about this as well. So I talked about how we need more better neutrino cross-section data, and DND we are starting in high precision, high statistics data, constant physics, but we also need data from external sources. For example, where you can have more clean probe. For example, electron scattering. So electron scattering, like a JLab, we have electron beam, you can scatter from our nucleus. Of course, in one case, it's an electron scattering of the nucleus, it's electromagnetic scattering. While in the neutrino scattering of the nucleus is a big process, but electromagnetic process the nuclear current is vector. While in the neutrino case, it's the big current is a vector minus axial, and the vector current is conserved between the both processes. So one could actually constrain the nucleus at the vector nucleus, nuclear effects, effect, as well as vector current by just doing electron scattering experiments. Electron scattering providing non-radiating beam, they make a very precise. We can do that. We have the beam which was 2.222 G, which that's how precise we knew the number. Yes, also one could actually use elements from there to constrain big part of our model. This is what we have been doing. We have been a lot of the data in electron scattering for decades, but in recent years there some proposals, some have taken data and others are proposed at JLab, SLAC, and mines. They are driven by internal physics. So they are not driven by solving some nuclear problems. They're driven by how can we, use electron scattering to physics for doing. And so here, and these experiments, if you look at this is omega versus Q, energy movement transfer, nucleus map, A is the Dune coverage, and this covers all the experiments. So if we were able to take all data here, the constant big part of cross section. Example of this experiment, the top one here. So that's the only one which these people have already collected data at JLab, and the one who already produced the results on organ nucleus. This is the experiment at JLab. We have the sun beam 2.222 GeV size here, and you have the organ target here. You can smooth that whenever you want. So if we fix certain angles for the vector function of the nucleus, and also to measure cross section, and we measure the first cross section on organ E prime, so inclusive cross section, and measure the vector function, so the missing energy and momentum spectrum of the organ nucleus. All the spectral community of JLab and so on is also helping to improve this process. In the last slide, so I come back to here. This problem is very complex. People are working in different parts of the field and trying to work together, and some of us are working on these things called this problem. That help us with more funding. Back in the support, we talked 10 years ago, people would say we don't need to solve this problem, it's a bigger issue. But now the community is kind of convinced. Short summary of a long talk. It's now the largest source of opportunity in the accelerator program. Both have low energy as well as the G sources. We need dedicated cross community efforts and sustain them to achieve the global constant that we need for neutrino-nucleus cost physics. there have been significant development in the last few years, all fronts. Lot of work to be done before the start of Doom, if you want to achieve the required precision. Thank you so much.
Any questions?
Can we go back to your that Marley plus CRP? The right plot is based on Marley plus CRP.
So the version 1.2.1, all the dashed lines are the old model. All the full lines are part of the CRP. So the old model and all the full lines are after we get at CRP. They give the total process limit, they give the return fraction a lot.
By any chance, do you remember the shell model of the CRPA for those points? The shell model is a little bit on the lower side, so I'm wondering whether if you put two shell model, not only
Yes.
shell model plus CRPA, then maybe it looks different.
This had obviously the protocol and useful.
Right.
So TRP here, the blue one. Black is the Pandey. TRP, I think this is cell model with RB. This is what I don't know the.
But again, then at the end of the day, it's kind of comparing one simulation with another.
Exactly.
But can you not use like some existing data from Carmen, some Xenon experiments so we have done?
This is all I did is there is in the world. I improved out over last 2 years. All we have. This is the value from carbon, right? So CRP actually describes so the
Yeah, it's a carbon.
yeah, I think CRP describes the measurement was made by in from at the time when this carbon measurement came out end of 1998 or something. So we are in CRP describes the and also yeah, that's actually a key point as well because when I mentioned this thing, the annular thing, the black line, if you have CRP, it shows that word strength. If you go back to this paper, from both from LSMD and Carmen, they have this kind of plots, angular plots, and it looks like this. So the
Remember, shell model also has that.
exactly. So I remember in particular LSMD data. I think it sent me that also has this kind of shape, and they have the flat line.
So that's why I wonder if you combine shell model plus CRP, probably.
Parallel market. Could be more measurements. One place is CCM. They can make measurement also at lab up to do.
Oh, we did some xenon measurement recently.
On lead.
You know.
Iodine, but maybe there was Gen on after. This was after 2023. Maybe something was last year, or maybe something.
Yeah, actually, I saw some.
They dropped their xenon, right? Oak Ridge.
Yeah.
They had issues with their xenon. They were going to do it. Oh, yeah.
Xenon detector was gonna come to.
No,
why
that's
they
the
dropped
issue.
it.
Yeah, but remember.
Yeah, I know what you're talking about.
So they did the timing measurement on, you know.
Sorry, we're.
We had to talk, so that.
Yeah.
Maybe there's a plan, but I don't think I've seen
Yeah,
the.
then I checked, there is a PRL paper, and where they did the timing measurement for late.
Yeah, and I know. Leonardo?
Yeah,
Yeah, Brian Leonardo. Yeah.
They have to do delay because new is come from delayed, right? And new is-
McDonald.
No, so the thing is, there is a prompt de-excitation photon.
I see.
There is a delayed de-excitation. So they were trying to catch both of them. Back to the xenon detector, and that was the. Yeah, so that then I realized that they have some xenon.
RPA. How high energy is going to anti-MU, 30
You
MU?
can go to GeV, the same model, the coordinate thing as well. So if I go back to my early,
From
propaganda slide, the CRP starts from the south. We can do wave that's great, then we can continue gas analysis and the galactic peak under that. So CRP, I think it's the only model in the community which can do anything from first solid to here. In the same quantum mechanical model, we don't do any separation of state and so on. And we now we have again we're working on adding this part. It's called iterating, where we have access connection with add this as well. So in the future, 3-4 years, this is we will have CRP moving here as well. So there is no end. We could go until GED.
If we use this term method.
And the SCARMs actually gets very strong for high enough energy because it's basically fitted to the low ground state properties. So we need to have the form factor to control. This is a SCARM, right? We also use a SCARM to calculate this side, and then the other goes here. And this potential is fitted to, it's similar to argon V18 and so on, right? It's fitted to mass table or whatever of ground property. But that's only from high energy, so we have some use by factor to control it. And as you see here, this is all from CRP. This is GeV energy. Right. So it has both the low acceleration. That's it's also in Gini now. CRP. So people